In the previous video, we introduced the direct synthesis method, which is a method of controller tuning where we choose the servo transfer function and then solve the servo transfer function for the controller settings. We found that a convenient choice for the servo transfer function is an FOPTD model. If the servo transfer function is an FOPTD model, and G tilde, our model for the process valve and measurement, is also FOPTD, then the direct synthesis method gives rise to a PI controller with 1 degree of freedom, the time constant for the closed loop feedback servo transfer function. Similarly, if G tilde is an SOPTD model for the process valve and measurement, then the direct synthesis method gives rise to a PID controller, where again, the one adjustable parameter is tau c, the time constant for the closed loop feedback servo transfer function. We also found that when G tilde has a right half plane 0, this creates an unstable pole in GC. So we need a method for dealing with that. The IMC method generalizes the direct synthesis method and offers a strategy for dealing with right half plane zeros in G tilde. We first factor our process model into 2 parts we'll call G tilde plus and G tilde minus, where G tilde plus contains the time delays and any right half plane zeros, and it has a gain of 1. G tilde minus then contains everything else, including left half plane zeros and all of the poles of the G tilde model transfer function. Then we define the IMC controller transfer function as the reciprocal of G tilde minus multiplied by f, where f is a product of denominator time constants. Because the controller transfer function, which we call here GC star, does not contain the time delays or the right half plane zeros, all of the problems have been removed. This function f, which is a product of time constant terms, is referred to as a low pass filter. We'll understand the meaning of this terminology when we study the frequency response later on. Usually we choose r equal to 1, but r might be an integer larger than 1 if that's necessary in order to make GC star physically realizable. If r is equal to 1, then this term simply becomes a first-order filter. The IMC method gets its name from one block diagram representation of the feedback control loop that uses the IMC controller. The standard feedback control loop that we've looked at so far can be simplified and represented this way, where remember that the transfer function G shown here contains the process transfer function, the valve transfer function, and the measurement transfer function. The IMC controller, on the other hand, can be designed with a little bit more complicated transfer function that looks like this, where the signal being sent to the valve, P, is also sent to an internal model called G tilde. G tilde predicts how Y, the controlled variable, should respond to changes in the controller output. The difference between how the controlled variable Y actually responds and how we expect it to respond, which is Y minus Y tilde, is the signal that gets fed back to the controller to compute the error signal. In this way, the signal that gets fed back to the controller contains any effects of disturbance variables, as well as any errors in G tilde. You should be able to show that the block diagram shown here gives rise to this servo transfer function, where changes in the set point affect changes in the controlled variable by the product of everything in the forward path between the set point and the controlled variable, GC star times G, over 1 plus everything in the feedback loop, where now everything in the feedback loop is GC star times G minus GC star times G tilde. If we set these two transfer functions equal to each other, then we can find out how to relate controller tuning parameters for GC in a standard feedback control loop to the corresponding settings that we would obtain if we were using the internal model method. We find that GC, the controller transfer function for a standard feedback loop, should be GC star over 1 minus GC star G tilde. Now we can tune a controller according to the IMC method and relate the resulting tuning parameters to the controller that we should use for a standard feedback control loop to obtain exactly the same behavior. In the best case scenario, our model G tilde which remember we factor into g tilde plus and g tilde minus, is exactly equal to the transfer function g, representing the behavior of the valve, process, and measurement. If g tilde is equal to g, then this term goes to 0, and the servo transfer function will be gc star times g tilde minus times g tilde plus. Remember that gc star is the reciprocal of g tilde minus times f. So if we substitute that back in for gc star, we're left with g tilde plus multiplied by our first order filter for the servo transfer function. Remember, we said earlier that g tilde plus has a gain of 1. Therefore, our servo transfer function will also have a gain of 1. And when the process reaches a new steady state, the controlled variable will be equal to the new set point. In general, we want to choose the tau c, that is, the time constant for the filter term, to be less than the dominant time constant in g and greater than any time delays that might be present in g. In this case, the controlled process will then respond faster than the open loop process, but slower than any time delays. If it were to attempt to respond faster than the time delays, then it's likely that the process would become unstable. Since both the direct synthesis and the internal model control methods give analytical expressions for the controller transfer function, you can use them to derive PID controller settings for common classes of process dynamics. Some of them are given in Table 12.1. For example, for second-order processes without time delays, either written in the gain and time constants or the polynomial form, we can look up the controller settings in Table 12.1. Remember, k, tau 1, and tau 2 are determined by the model for the process, g, or alternatively, k, tau, and zeta are determined by the model for the process, g. So the only adjustable parameter here is tau c, the time constant that we choose for the closed-loop servo transfer function. Table 12.1 contains a menu of different types of models that we might choose for g. These include familiar things like first and second order transfer functions, FOPTD, and SOPTD models that contain numerator dynamics. For example, if you have an SOPTD model that does not contain numerator dynamics, you can use entries I, j, k, or l as appropriate, just setting tau 3 equal to 0. Now, when we developed the direct synthesis method, you may recall that the time delay in the model, either of an FOPTD or SOPTD system, results in a time delay in the denominator that we said could be approximated by a first-order Taylor series expansion. Using the first-order Taylor series for the FOPTD model gives rise to entry g in this table, and for the SOPTD model gives rise to entries I and j. However, if we use a different approximation for the time delay, then we end up with entry h for the FOPTD model and entries k and l for the SOPTD model. This table also contains interesting transfer functions that we may not have looked at yet, such as an integrator plus time delay model in entries m and n, and an FOPTD model multiplied by an integrator in entry o. Because the IMC method is an extension of the direct synthesis method, Table 12.1 includes the equations for the direct synthesis method. Care must be taken when using the DS or IMC methods for models that have very small time delays. That is, a time delay theta much smaller than the dominant time constant in the process tau. These models are called lag-dominant models, and will often have integral times that are too large, resulting in what we call sluggish responses to disturbances. Remember that the IMC and DS methods are based on the servo transfer function. So while the servo transfer function or set point changes will give rise to desirable behavior, the regulator transfer function or the response to disturbance inputs may not be so well behaved. This plot shows the response of a controller tuned using the IMC method for an FOPTD process model with a time constant 100 times larger than the time delay. You can see that the set point response looks very reasonable. The time constant for the process model is 100 time units, but when there's a unit step input to the set point change, a well-tuned controller can achieve a comparatively very rapid set point response that settles to the final value in less than 10 time units. However, a step disturbance into the same feedback control loop results in very poor disturbance rejection. It takes much longer for this process to reach the final steady state value in response to a disturbance input than it does in response to set point change. Two ways of dealing with such lag-dominant models are to use what's called the integrator approximation method, where G tilde is modeled by ignoring the constant term here, and instead we tune this as an integrator plus time delay model, or by using the Skogestad modification of the IMC method, called the Skogestad IMC method. The Skogestad IMC method modifies the value used for the integral time by choosing the minimum of either tau or 4 times tau c plus theta. Here, the reason why this process model takes so long to respond to disturbances is because this model would have a very large integral time chosen equal to tau. If instead we use the Skogestad method, we get a much smaller integral time. And the Skogestad method, as you see here, can obtain much better disturbance rejection. However, it sacrifices a little bit on the response to set point changes. The integrator approximation provides even better disturbance rejection, but higher overshoot in the case of set point changes. In the next video, we'll look at some other tuning relations that can be used to tune feedback control loops.